Alright, this is lesson 2.1, functions and equivalent algebraic expressions. And you have a little warm-up activity there just to get you to think about it a little bit, but consider a system of linear functions. So what was a system of linear functions again? Any idea? What constitutes a system of linear functions? You don't have to write it, but two functions where both equations are linear. These are both linear functions. This one's in the form y equals mx plus b. This one is not, but that's okay. It's still linear. What possible number of intersections could they have? Well, this is a line, and this is a line. What possible number of intersections could they have? Just one. Any other options? What if this is the line and this is the line? 0. Any other options? Just one more option. What if this is the line and this is the line? Infinite. Okay, 3 possibilities. 0 intersection, 1 intersection, or an infinite number of intersections. What does each possibility tell you about that system of lines? What do we know about each of these possibilities? What are the 2 lines that make up the system that never touch? What do we know about them? Those 2 lines are parallel. If they just cross each other once, we just use this word, intersecting. That means they're not parallel, they're not on top of each other. Any 2 lines that are not parallel will cross each other once, at some point. Okay? And if they're infinite, what does that mean? They're constantly intersecting. What does that tell us about the 2 lines? They are the same line, so we're going to use the word equivalent. Equivalent. It's an equivalent function. It's an equivalent expression. Good. Well, now what about a system of 2 non-linear functions? How many times would they have to intersect to show that they are equivalent? If they intersected once, could they be considered equivalent? Twice? 3 times? 4 times? What about these 2 functions? 1, 2, 3, 4, 5, 6, 7, 8. And it keeps going. Are they equivalent? They're not. It's very difficult to show on a graph if they're equivalent or not, but to do it algebraically, all we have to do is get both equations to look the same. And then we can say, oh, they're equivalent, or they're the same. So this doesn't prove anything. We need to be able to see it algebraically. So we're going to walk through today is a couple of methods for determining whether or not 2 functions are equivalent, and we get into that in example 1. You have more space for notes. Maybe we should take more notes. Let's just leave that blank and we'll come back to those notes. Yeah? So, example 1. Determine whether the functions in each pair are equivalent by 1. These are the 3 methods. We can test 3 different values of x to see if they're equivalent on all those different values, and maybe we could say that the functions were equivalent. Then we could simplify the expression on one side, or we could graph using graphing technology. So the first one is, and you might have to write a little bit small. Obviously 3 graph using graphing technology is not going to take up any space, but you might want to just work down the left column maybe for A and the right column for B, unless you prefer to split it up top and top. However you do it, you need to get 2 examples in that space. So we're going to test 3 different values of x to see if to see if f of x equals 2x minus 1 squared plus 3x minus 2 and g of x, which equals 2x squared minus x, are equal. So what values of x do you think we should test? I'll give you a tip. Choose the 3 easiest values of x you can think about. For me, those are going to be, and I'm not going to write them in here yet, but just so you know what we're doing, we're going to do negative 1, 0, and 1. They're all acceptable values of x. We're going to sub them in to f of x, which is 2x minus 1 squared plus 3x minus 2. And then we're going to sub them into g of x, which is 2x squared minus x. So the thought behind this is, if we get the exact same output in f of x and g of x for each of our inputs, is that enough to say that these are equivalent relations? What do you think? If we put in x equals negative 1, 0, and 1, and we, in f of x and g of x, we get the same output each time, is that enough to prove that these are equivalent relations? Yeah? Maybe? Not sure? Possibly? Let's find it. So let's sub in first negative 1. So we're calculating this function at the point x equals negative 1. And we're just going to sub in negative 1 everywhere we see x. And we can start to simplify. Using bedmass inside the brackets, we have minus 2 squared. 3 times negative 1 is negative 3 minus 2. Keep working this down. I'll take longer on the first ones while we're getting the hang of it, and then I'll go a little bit faster on the other ones. But now we're dealing with the exponent. So here we have 4, negative 2 squared is 4, times 2 is 8. And here we have plus, but in the bracket we have negative 3 minus 2. So that's going to be plus negative 5, which is just minus 5, which is 3. Well, let's see what happens to g of x. In g of x, we're going to sub in negative 1 for x. We're going to have 2 times negative 1 squared minus negative 1. So be very careful with that. You've got a negative x, but we're putting a negative 1 in for x, so you've got 2 negatives there. So here we have negative 1 squared, which is positive 1, times 2, that's 2. And negative negative 1, or minus negative 1, is positive 1, which is 3. So far, so good. 3 on both. Let's try 0. So we're going to sub in 0 to the function f of x. Everywhere we see an x, we're going to put 0 instead. Do that very carefully as you're putting things in so that you've copied it correctly. And then we follow it down. I'm going to do more steps at once here. 0 minus 1 is negative 1. Squared is positive 1 times 2 is 2. 3 times 0 is 0 minus 2. When you sub in 0, you get 0. Let's try g of x. And again, these are the examples that after we copy it down, you should be trying to do the algebra in your head as fast as me. And then me saying it or writing it down should be kind of like double checking your own answer. We got 2 times 0 squared minus 0. Well, that all just is 0. 0 times 0 is 0, minus 0 is 0. So far, we're looking equivalent. See what happens when we sub in 1. F of 1 to 1 minus 1 squared plus 3 times 1 minus 2 And we can do that down. 1 minus 1 is 0. 0 squared is 0. 0 times 2 is 0. And then we've got 3 minus 2 is 1. We got 0 plus 1 is 1. And over here on the right in g of x, we've got 2 times 1 squared minus 1. 1 squared is 1, times 2 is 2. That's 2 minus 1 is just 1. What does it appear that we have in the two functions from A? They appear to be equivalent. So based on our calculations, comma, f of x and g of x, f of x and g of x appear to be equivalent. However, 3 examples don't actually prove that the function is equivalent for every value of x. Yes?
Why didn't you sub in 0 and 1 for g of x?
Yeah. Like that?
Yeah, does that change?
Doesn't change anything, I just didn't write it in. But yes, I should have written that in. We calculated g of 0, the value of the function g when x is 0. Then we calculated the value of the function g when x is 1. Yep, good catch. Okay, the next step is to test whether or not they're the same by simplifying one of the functions in the pair. Okay, so we're going to use the same 2 functions, which are right here. But in step 2, we're going to do this by simplifying each function. Now, g of x is already simplified. I can't simplify that any further. So I'm just going to leave that. And we're going to simplify f of x. And when we do, we're going to see if we get the exact same expression on the left and on the right. So how would we, what would be our first step for simplifying this whole expression? What do you think we should do? Inside the brackets, can I simplify anything inside these brackets? Can I simplify x minus 1? No, they're not the same. I'm dealing with x's and constant. Same thing here. I've got 3 x's and minus 2 constants. Nothing to do inside the brackets. Exponents. Yep, I got an exponent here. X minus 1 squared. So if I need to, I could pull that to the side and FOIL the whole thing. But because we've been doing so much work with, special products, things like that, we know that this is going to end up being x squared minus 2x plus 1. And we'll keep the rest the same, so we're going step by step. If I were doing this on my homework, I'd do some things at the same time, like I would have, I already would have simplified this thing, which I actually did. But anyway. Division and multiplication, here we come. So this 2 gets distributed to all of the parts of the bracket that's attached to it by multiplication. So we're going to end up with 2x squared minus 4x plus 2. And then here, this 3x minus 2 is in brackets, but it really doesn't need to be, because it's just plus 3x, and if we distributed the plus sign to over there, you'd still have minus 2. So this is just going to be plus 3x minus 2, no brackets. What's next? Can we add and subtract? We have like terms. Yeah, if I'm ever doing like terms, I like to just kind of underline my like terms. There's a squiggly line under my constants, a straight line under my terms involving x. I only have one term using x squared. So we've got 2x squared and I've got minus 4x's and plus 3x's. So that's minus an x. My constants cancel out. What do you notice? That equals g of x. So we can say algebraically, comma, these functions are equivalent. Okay, so just testing 3 points isn't enough to confirm that they're equivalent, but if you can algebraically simplify and reduce one of the equations to be the exact same as the other one, then you know that the functions are equivalent. We'll take a second now just to quick graph it on Desmos, and then you can see that they are. Go ahead and take a look at the two functions in B, and just take a guess to see if you can kind of figure out in your head if they have anything in common or if they're equivalent. And what do you think? Okay, so we are going to test our 3 points for the two functions in B. We're going to do that the exact same way that we did it in A. So we've got B, step 1, we're going to just test 3 points. First of those points being negative 1. And we're first going to put it in f of x equals x squared minus 2x minus 8. It's also super helpful if while I'm doing this you guys kind of double check that it's the same. I'm actually writing the same thing that you have in yours. X squared minus x minus 12. And before I cover anything up, let's try and do that. This is also really good practice for you're finding the value of the function at x equals 1. So when we're making ordered pairs essentially, whatever we get down for our answer down here at the bottom, the ordered pair on the graph that the graph goes through will be whatever we get for f of x paired with x value of negative 1. So you should be able to do this pretty straightforward. So we're finding the value of the function at negative 1. So everywhere we see an x, we're going to sub in negative 1. Being careful with our negative signs here, we're going to have an adding 1 rather than subtracting 1. And then work it down. So we can do as much or as little as we want in each step. We're going to go negative 1 squared is positive 1 in the numerator. Then we've got negative 2 times 1, negative 1, that's positive 2. Then we're subtracting 8. And in the denominator, we've got negative 1 squared, which is 1. We've got minus a negative 1, that's positive 1. And we're subtracting 12. And to reduce that, we've got plus 3 minus 8, that's negative 5, over plus 2 minus 12, that's negative 10. So negative over a negative is a positive. 5 over 10 is 1/2. Positive 1/2. And we're going to do the same thing in g of x, which is a little easier. We've got x plus 2 and x plus 3. And we've subbed in negative 1, so we're finding g, the value of the function g at negative 1. So we've got negative 1 plus 2, negative 1 plus 3. That is 1 over 2. Same. We are going to sub in the value 0 to each function. So f of 0 is 0 squared is 0, negative 2 times 0 is 0, and we're just going to be left with negative 8 in the numerator. And yeah, I'm reducing quickly. In the denominator, you're going to have 0 squared minus 0. It's all still just 0, and then we're going to have minus 12 in the denominator. So this reduces to, what does this reduce to? Yeah, positive 2/3, because we got a negative over a negative. And then we're looking over at g of x, which is now going to be g of 0. So we've got 0 plus 2, that's 2 in the numerator, and 0 plus 3, that's 3 in the denominator. And that one checks out. They are equivalent.
You scroll up just for this. Yeah, I'm at the beginning.
Like in this box?
No,
Okay, that's okay. Okay, hopefully you've given calculating that out a good shot on your own. You should have gotten that the value of the function f of x at x equals 1 is 3/4, and that is the same for the value g of x. So, after testing 3 points, it looks like these are equivalent expressions. Let's go ahead and try step number 2, where we simplify the more complicated expression and see if we can express it in the same terms as the already simplified expression. So I'm going to clear what I have here. Am I good to clear this? Yeah? I'm going to leave these guys up here. Looks like g of x is already simplified. So we're going to see if we can get f of x to look like g of x. And if we can, then we can say they are equivalent equations, equivalent functions. So what's one step, do you think? Do you have any remembrance or any idea what we can do to simplify this thing?
I like terms.
Do I have any like terms in the numerator? Nope, I've got x squared, x's, and constants. And in the denominator I have x squared, x's, and constants. So you might be tempted to be like, oh, these guys just divide out. And it's the second time I did that today. And negative 2x divided by x, oh, that's just, that's negative 2. Or positive 2, sorry. You can't actually do that. It doesn't work that way. Anything in the numerator is grouped together. So you can't just go in dividing bits and pieces of it by bits and pieces of the denominator. So what we actually need to do here is factor the numerator and the denominator, and then see if there are whole groups of terms that can cancel each other out, if there are factors that can cancel out. So if we're using our sum and product skills to factor the numerator, we've got a sum of negative 2, product of negative 8. What numbers will successfully factor that? I could list all the factors of negative 8. I'll just go straight for the easiest ones. They're 4 and 2. And they have 2 in common for sure if I'm adding them, but which one of them has to be negative, the 4 or the 2, in order to end up at negative 2? If you're not sure what's going on, basically we've said the 2 numbers that we choose to factor this. So here's our numerator. We're going to have x something and x something. And the 2 numbers that we choose are going to multiply to negative 8. So I know that one of them has to be positive, one of them has to be negative. And they're going to add to negative 2. So that tells me that the larger value has to be negative. So now negative 4 times 2 is negative 8. And negative 4 plus 2 is negative 2. So this will successfully factor the numerator. We've got x minus 4 and x plus 2. In the denominator, I'm going to do the exact same thing. I need to factor it. So in the denominator, we have a sum of negative 1 and a product of negative 12. Well, what 2 numbers are going to multiply to 12 and have a difference between them of 1? 3 and 4. Now, because it's negative 12, the product, I know one of my factors has to be negative. Which one is it? Well, it's the one that's going to help me when I add them up. It's going to end up resulting in negative 1. So which of these is negative, 3 or 4? 4 has to be negative. So now we've got x minus 4, x plus 3. Well, what do you see here? Since this is all multiplication and division, I can actually cancel out these factors. Okay, if that doesn't make sense, just take this as a little side note. It's kind of like if we said, if I had 2 times 3 over 2 times 4. Well, this is 6 over 8, which reduces to 3 over 4. But we could do it this way as well. We could say, okay, these cancel each other out. which leaves me with 3 over 4. Same principle is at play here. What cancels out in the numerator and denominator? Do I have a same factor in the numerator as I have in the denominator?
4.
X minus 4. Okay? So these guys just become 1 and 1, which leaves me with x plus 2, x plus 3. X plus 2 over x plus 3. Is that looking a lot like g of x? This is where it's going to get a little bit tricky, but for now, we're going to say, algebraically, these functions appear to be equivalent. Algebraically, these functions appear to be equivalent. But go ahead and graph it on Desmos if you're watching this on your own. Otherwise, we'll do it right now in class, and we should see that they're actually not perfectly equivalent. There's going to be a gap in the function f of x. So when you graph these two functions on Desmos, they look identical, they look exactly the same. They both have asymptotes at x equals negative 3, but when you zoom in on x equals negative 4, sorry, x equals positive 4, on the function f of x, you realize that there's actually a little gap right there. It's undefined at the value x equals negative 4, because if we were to sub x equals 4 into here, we'd get a denominator of 0, which results in an undefined number. Now, they canceled out, so it's not an asymptote. We still have an asymptote at x equals negative 3, but it is a gap, whereas g of x doesn't have any gaps. It has the same asymptote, but no other restrictions on the domain. So if you flip back to your notes that we can write on the first page, the notes from the first page, and we're going to write a couple things. We're going to say polynomial functions, polynomial expressions. Polynomial expressions that can be algebraically simplified. Polynomial expressions that can be algebraically simplified to the same expression. So you can simplify them and they become the same, are equivalent. However, with rational expressions, so a polynomial expression, maybe we can just give ourselves a little reminder of what a polynomial expression is. That's anything in the form of ax to the power of n plus, well, we'd say a1, a2, x to the power of n minus 1, a sub 3 to the power of x to the power of n minus 2. So it just means that, let's say you were starting with x cubed, the next term would be x squared, the next term would be x, the next term would be your constant. This goes all the way until you get to just your constant. That's an example of a polynomial expression. Like a linear expression is a polynomial, quadratic is a polynomial, cubic is a polynomial. We'll discuss what rational expressions are in a second. However, with rational expressions, this may not be the case. You might get two rational expressions that you can reduce and simplify algebraically down to the exact same expression, and yet they still might not be equivalent. They might not be perfect. So, what is a rational expression? Rational expression. This is the quotient of two polynomials. Quotient of two polynomials. So it's p of x is one polynomial and q of x is another, and it would be p of x over q of x. And the rule for this is that the function q of x can never equal 0. Wherever it equals 0, the graph will be undefined. And that's what we ran into in example 2 with our, example 1 with our restriction. We'll continue on using that same example. So in example 1, we started with, let's maybe write this for example. In example 1, we had this function. We had f of x equals x squared minus 2x minus 8 over x squared minus x minus 12. And we reduced this to, we factored it, and we ended up with x minus 4, x plus 2 over x minus 4, x plus 3. Okay, that's all work that we've already done. But our definition for a rational expression says that the denominator can never equal 0. So we want to find out what values of x would make the denominator equal 0 and say, hey, you can't do this. Okay? So I'm going to just go off to the side here, and we're going to say, okay, if x minus 4 equals 0, that's going to be a restriction. And where x plus 3 equals 0, that's going to be a restriction. Because if this factor equals 0, the whole denominator will equal 0, and if this x plus 3 equals 0, 0 times anything is 0, that will make the denominator equal 0. Some of this should be quite familiar. We're going to add 4 to both sides. That tells us there's a restriction at x equals 4, which we found. That was a gap. And here there's a restriction at x equals negative 3, which we found it was still an asymptote. So if we were going to reduce this, we can't just cancel these guys out. If we do that, we're not showing the second restriction on the domain. So what we need to do is write it in its simplified form of x plus 2 over x plus 3. And then right beside it, we need to note its restrictions. X can't equal negative 3, and x can't equal 4. Now, this is a proper simplified rational expression. One thing about this is, and in grade 12 we actually don't do this, this restriction is already noted right here. Right? This tells you that it can't be, x can't be negative 3. This restriction we really need to make sure that we record here, because that's the only place it's recorded. This work all gets canceled out, crossed out, whatever. But this needs to be here with this one, and in grade 11 for some reason we include that restriction as well, even though it's already kind of stated right there. Good. Okay, so that rational expression stuff should be fairly new. Now we're just going to practice it and identify our restrictions. So we've got, in example 2, we have A. It says we're going to deal with the expression x squared plus 10x plus 21 over x plus 3. We need to simplify each expression and determine any restrictions on the variable. Can I simplify the denominator? Nope. Can I simplify the numerator? Probably. Sum and product. 10, product of 21. Can you think of any two numbers that have a product of 21 and add to 10? Nice. 7 and 3, both positive. That's easy enough. So my numerator becomes x plus 7, x plus 3. Yes, if we multiplied this thing out, if we distributed it and FOILed it, it would get the exact same expression that's there. In the denominator, we have x plus 3 still.
Where'd you get 7 from? I mean
This? Came from the problem, but 7 plus 3 is 10. 7 times 3 is 21.
Oh,
Sum is the answer to an addition problem. That's okay. So what happens to the terms here? We have a common factor in the numerator and denominator. So these guys actually divide each other out. We're just left with x plus 7, but we have to remember that there's a restriction where? What can't x equal? Close? Negative 3. Okay, if x were negative 3, the denominator would be 0. So the way to find that out is to say, okay, there's my denominator. Wherever it equals 0, I'm going to have a restriction. Subtract 3 from both sides. I have a restriction. This is where the restriction is, so you should maybe rewrite it like that. Okay, my denominator can't equal 0, so x can't be negative 3. What do you know about this function? Look familiar at all? If you were to draw it, what would it be? Would it be a curve or a line or a squiggle or a circle? It's just a line, right? It's just a line, but wherever x is negative 3, there's a gap. Can't equal that. Okay? Good. Let's check out B. B says 6x squared minus 7x minus 5 over 3x squared plus x minus 10. Now this factoring gets a little bit trickier, so I'll do a little bit of work on the side, but we have to factor both of these. Do you remember how to factor things when a isn't 1? We're still using sum and product, but this time it's not going to be able to go straight into our factors. It's just going to split the middle term, which is actually what it does when a is 1, but we skip that step. So we have a sum of negative 7, and we have a product of a times c, which is negative 30. Okay, so now we're looking for two numbers that will multiply to negative 30 and add to negative 7. The values are 10 and 3. Which one is positive? Which one is negative?
3 is positive.
3 is positive. 10 is negative, right? The larger number is going to be the negative number. Negative 10 plus 3 is negative 7. So in the numerator, all that does, and again, I'm just going to do all this work kind of off to the side because I don't want it in what we're doing. We've got 6x squared minus, sorry, I'll switch it around because it's easier. I'll go 3 plus 3x minus 10x minus 5. So all we did is we substituted these guys in for negative 7x. Okay? Now I can factor by grouping. So I can group these first two terms together. Say, okay, I can pull out 3x, leaving me with x plus 1. And here I can sub out negative 5, pull out negative 5, factor out negative 5, leaving, oh, I made a mistake, 2x plus 1 here in this first bracket. And same thing in the second bracket, 2x plus 1. Now again, we've got two terms. We've got 2x plus 1 is a factor of each term, so we can factor out 2x plus 1. If I pull it out of this term, it's going to leave me with 3x. If I pull it out of this term, it's going to leave us with negative 5. So that's the factored form for our numerator. 2x plus 1, 3x minus 5. In the denominator, we'd use the exact same strategy. We'd be doing sum and product with a sum of positive 1 and a product of negative 30. I'm not going to do the work. I'm just going to write down what you would end up with. You'd end up with 3x minus 5 times x plus 2. Now, what do you notice about the terms in the numerator and the denominator? Can anything cancel out?
The 3x plus 5 on top of 3x plus 5 on the bottom.
Okay, we've got 3x plus 5 in the numerator and in the denominator. Sorry, 3x minus 5. Is that better? So we can cancel them out. They both equal 1 over 1. So this thing reduces to 2x plus 1 over x plus 2, but we can't forget the restrictions that we just found. What are they?
X can't equal or
So we know x can't equal negative 2, and actually a really good way to do it, guys, is in this step, while it's still all here, and you have both of the factors in the denominator still, just say, okay, x can't be negative 2, and the other one is a little bit trickier, but we could do that work off to the side again. 3x minus 5 can't be 0. 3x can't be 5. X can't be 5 over 3. Okay? So our other restriction is x can't be 5 over 3. Now that one I'm going to take down with me here. Okay? Because that one's not already represented in the rational expression. This one, if I was going to graph this expression and set it y equals this, you'd end up with an asymptote at negative 2, okay, a vertical asymptote at negative 2, and a gap at 5 over 3. Okay, example 3. Simplify calculations. It gives us instructions, and we're going to draw a little diagram to help us. A square of side length 7 centimeters is removed from a square of side length x. Okay, so let's draw a little bit of a bigger square. Doesn't have to be huge, just kind of off to the side. And it has side length x. And out of that square, we're going to cut another square. It doesn't matter where you put it or how you draw it. Doesn't matter how big it is. Nothing really matters. It's got side length 7 centimeters. We're going to pull this blue square out of the orange square, and we have to develop an expression that says that that's what we're going to do. So A, we are going to call this the orange area or the shaded area. So this is our shaded area. We need the area of the shaded area, whatever's left over after we pull out that blue square. So we've got the area of the large square. Sorry, let's do it this way. We're finding the area of the shaded. So area sub shaded is equal to the area of the large minus the area of the small. So far so good? Okay, how can we represent the area of the large square? Side length is x. The area is length times width. Or in the case of a square, it's width squared, or length squared. So what's the area of the orange square? And the area of the small square? 7 squared. And we can simplify that. X squared minus 49. Okay, so the shaded area should be x squared minus 49. Not too difficult. B says, okay, now write that area function in factored form. Well, you should be able to look at this x squared minus 49 and say, oh, it's a square, so they're square numbers, so I actually have the difference of squares, right? A squared minus b squared. Do you remember what that results in? Nice Pythagorean theorem. A squared plus b squared equals c squared. Here we have a squared minus b squared. So not quite the same thing, but this reduces to a sum and a product. So the product of a sum and difference. So this is x plus 7 times x minus 7. Hopefully it looks a bit familiar to you now that you're seeing it. So that's factored. And then C says use both forms of the equation to calculate the area for x values of 8 centimeters, 9 centimeters, 10 centimeters, 11 centimeters, 12 centimeters. You're not going to do that, but if you had to guess, which one is easier to use if you're doing mental math? So you can use this form or this form, and you need to test for values of x equals 9, 10, 11, 12. Which form of the equation do you think would be easier to use? This one with a difference of squares, or this one with the product of a sum and a difference? Let's vote. Gavin, which one? This one or this one? Which one's easier to use if you had to sub in a value for x? So would you rather do 81 minus 49, or would you rather do 16 times 2? So Gavin picks this one. Emma? Vlad?
Factors.
Yeah, that's my vote too. That one's easier to use when you're doing mental math, right? This one looks shorter. It's not hard either. If you had your calculator, it's not hard. But mental math, this one's a lot quicker and easier. Okay, D. What is the domain of the area of this function? So when we're asking about the domain, we're basically saying, are there any restrictions on x? Can x be any value? What do you think? In a real life scenario, we're talking about area. Are there any restrictions on x? Can you have an area of 0? Or a negative area?
No.
You can't. Okay? And we need to be able to pull out the blue square. So what does x have to be at least? The orange square has to be at least bigger than the blue square. So what does x have to be?
Anything greater than
Anything greater than 7. Okay? We're going to take a little jot note there. Since this function represents area, it must be restricted. It must be restricted to x values that do not result in negative or 0 areas. Therefore, domain. All our values of x come from the set of real numbers. Okay, it doesn't have to be whole numbers. It can be decimals, it can be rational numbers, etc. But x must be greater than 7. Okay, that was all about determining if two expressions are equivalent. We just need to simplify both and see if they're algebraically the same. But then we also need to check for restrictions by determining where the denominator is 0. If the denominator is 0 at a certain value of x, then that can't be. The function is restricted. It can't. X can't be that value. And then we need to state our restrictions when we're rewriting expressions as well. Your homework is at the bottom of that page. Practice problems, page 83, number 1 through 8. Come to class tomorrow with questions.